Okay, this section lays down the foundation for the next section, which deals with buffer solutions, which are a really, really big deal in human chemistry as well as other chemistries, but particularly human chemistry is real important. So while we're going to study this, but we're going to do a few problems, just a handful of problems related to this, so you can understand the idea behind it. It's the next lesson that is really the big one. So to understand the common ion effect, we have to remember Le Chatelier's principle. And we talked about Le Chatelier's principle when we were dealing with equilibrium reactions. And basically an equilibrium reaction is like its own entity, its own system, its own way of fixing things that disrupt it. So if you were to externally bring in a compound onto a solution that is at equilibrium, you're going to disrupt that if one of the two ions of that compound that you add has an ion that's found in the mixture. And if that is the case, then that ion that now is being added onto the ion on the product side, because you've dissolved that compound, you've created these two ions, one of them gets increased, and that means the reaction is going to shift away from that increase, shift to the left, which means it's going to make that compound less soluble. Okay, and so what we are going to be doing is we're going to be looking at how, while K is going to stay the same, it's going to affect the overall concentration for that substance. Okay, so that's the idea here. We're looking at weak acids, weak bases as the compound that's being dissolved, one of the two, and then we're going to add one of those a compound with one of those ions in it that's going to cause it to shift away, and we're going to be able to predict how much change is going to take place, and we're going to be able to predict the new concentration of dissolvent, the amount of dissolvent that's going to take place as a result of that increase. So we're going to look at some odd number problems on page 763. We're going to look at 61, 63, and 65 to see how this manifests itself. Okay? Now, the first one talks about degree of ionization, and basically what that is saying is what percentage of the compound is going to dissolve into ions. And this is a really good problem to understand how this is going to be affected. What we're going to do here is we're going to look at the dissolving of just hydrofluoric acid by itself, nothing else added to it. And we're going to use that as a comparison for the next part of the problem. So what we're going to do here, HF, is a weak acid. It's not one of the 7 strong acids, so we know that this is double arrow. And we have a Ka given to us here that tells us it is indeed weak. And your product's going to be H positive aqueous or hydronium if you wish to think of it that way, and F negative aqueous. Now we're starting with 0.80 molar HF. I'll just put 0.8 here. Minus X here, we're doing our mini ice here, X here, and X here. Okay, so this is going to become X times X, which is X squared, over 0.8 minus X equals Ka 6.8 times 10 to the negative 4th. So we multiply 0.8 minus X to both sides. That's going to cancel out the 0.8 minus X in the denominator. And that's going to leave us X squared is equal to, and so 48 and 654, 5.44 times 10 to the negative 4 minus 6.8 times 10 to the negative 4x. Probably should double check my math on that. It's kind of a weird day. So let's take 6.8 times 0.8, and you get 5.44. Okay, I guess right. Okay, so and now I'm going to move the x squared over. So 0 equals negative x squared. We move that in front, minus 6.8 times 10 to the negative 4th x. Move this to the last part here because it has no x's in it. And now we're ready for a little quad form here. So go to program, hit your quad form, and type in -1 for A, negative 6.8 E, -4 for B, and 5.44 E, -4 for C. And we get our positive value for X is 0.0230 moles per liter. Now, what does X represent? Well, if we go up here and take a look, X represents both H positive and F negative, but the problem asks us to find how much is dissolving here. So all we really need is X. We don't need a specific value for that. Now, how do we figure out the percentage of ionization here? You take your amount that did ionize out from the hydrofluoric acid, 0.0230, divide it by the original concentration, which we said is 0.80. For both moles per liter will cancel out, times 100, and you get 0.230 divided by 0.80. You get 28.8%. Which seems kind of high, but I guess that's not, well, I forgot to put the point, so it's 2.88%. Got the 0. Yeah, what I mean. Okay, now, or they can express it without the percent, just leave it as 0.0288 without the times 100 in there. Scientists use both. But the 2.88%, that means just under 3% of hydrofluoric acid is going to dissolve when it's just in water. And we'll keep that in mind when we do the second problem of number 61, in which we're going to dissolve HF, which again, weak acid, in a strong acid of hydrochloric acid. Now, if we look at the fact that this is a strong acid, that's a single arrow reaction. That means it's going to completely dissolve into 2 ions, H positive aqueous and Cl negative aqueous. Okay, so the fact that we have 0.10 molar here, and this is a strong acid, it's going to break down completely, that's going to leave us no HCl when the reaction is completed, and 0.10 molar of the hydrogen ions and 0.10 molar of the chloride ions. Okay? Now, if we were to dump this 0.80 molar hydrofluoric acid into a vat of this stuff that has this concentration, the question is how much of the fluoride ion and the hydrogen ion at this point is going to break down. Well, we notice right away that we have a common ion. In fact, if I wrote that out again, which I probably should, HF double arrow, H positive plus F negative, and we have 0.8 minus X here, we have X here, and we have X here, we can see in the solution we have 2 compounds donating hydrogen ions to the cause, whatever the cause is. Brotherhood of Hydrogen Ion Society, I don't know. But what's important about this is that the chloride has absolutely no value to this whatsoever. It's done. Because it's just sitting there. It's what we call a spectator ion. But this is important. So what we're going to do is we're going to add 0.10 because that is the total concentration of hydrogen ions in solution when mixed with that. So now we have 6.8 times 10 to the negative 4 is equal to x plus 0.10 for the hydrogen, x for the fluorine, and then 0.8 minus x goes into the denominator. Now this is getting kind of ugly, but it has a point here. We're going to again multiply both sides by 0.8 minus x. And that's going to cancel out right here. And as we found before, this is 5.44 times 10 to the negative 4 minus 6.8 times 10 to the negative 4x equals, now I'm going to distribute that x across both of that, and that gives me x squared plus 0.1x. I'll drop the 0. This makes life a tad easier for us. So now I'm going to move, I'll move, well, let's see, I can move this over here, move this over here. Looks like it'd be easier to just move that. So let's just do that. So I'm going to subtract x squared and subtract 0.1x. Well, we have no x squared here, so I'll put minus x squared right there. But I'm going to add the negative 0.1x to this. And round that off to 3 sig figs. When I do that, I'm going to get negative 0.101x. Because that's actually going to be 0.10068, round off to 3 sig figs is 0.101. Okay? And I got negative x squared, and then this is going to go to the end over here, and that's going to set equal to 0. So you write that in a way that we can deal with on the quad form. Negative x squared minus 0.101x plus 5.44 times 10 to the negative 4 equals 0. Go to the quad form again. And I have negative 1 for A. I have negative 0.101 for B. I have 5.44 E negative 4 for C, and I get x is equal to 0.00513 molar. Now, before we do the degree of ionization, let's compare with the last problem what we had for x. And we had 0.0230 molar, but now we have 0.0513. We got much smaller, which is exactly what we predicted with Le Chatelier's principle. It shifted it a lot to the left. Now let's find the degree of ionization. We have 0.00513 divided by 0.8 times 100. And we get 0.641%. So it's dropped by about a quarter of what it was before. That's what happens with the common ion. And when we get into buffer solutions, that's a pretty common occurrence that we are going to be dealing with. Okay? All right.